So we are back. This is the answer number three of this assignment for the CML 661. We are comprehensively going to study about the X-rays. This assignment is submitted and being presented by sir. So the X-rays, we all have heard of X-rays. Whenever we have fracture or broken bones, we all go to our doctors and radiologists and get the X-rays done. The discovery of X-ray have been a bit miraculous, to be honest with you. So it is a very serendipitous discovery. There was this guy, this very, very famous scientist back in 1895. He was studying the cathode ray tube and how the beam of electrons that comes out of the cathode rays, how do they interact with the minerals and the different substances. And one day, what he observed that there was a piece of fluorescent paper which was lying along the cathode ray tube. Though it was very well known at that time that the cathode rays could not travel much more than few millimeters. But he observed that the fluorescent paper was fluorescing, even though it was way out of the cathode rays range. So it got him a bit intrigued. Though he didn't understand it completely, but he got some intuitions. There are some invisible rays that's powerful enough to travel through the air, and they're making it happen. He named them. He coined the term X-rays. X means we don't know, like what it is. Like it's kind of like enigma. So, and later it was like while they study, we all know that now we can see through the body tissues, bones, and materials which include X-rays. And X-rays had very high penetration power. They can even penetrate skin. So, to study all this, what he did is actually he took the first X-ray photograph of his wife's hand, and this is the first X-ray photograph that was ever taken. It was in 1901 when he got Nobel Prize for his discovery of X-rays and how it could be implemented in the medical field as well. And later it was studied that the X-rays have their wavelengths in order of few angstroms or less than angstrom. Now this was about the history of X-rays. Now we are going to study about how these X-rays are being generated in the laboratories for the purposes like we have to study the crystals in the medical field as well. So there's a very basic principle onto which these X-rays are being generated. Like very, very basic principle. What we do is to generate X-rays, we take electrons, very high velocity electrons, very high energy electrons, then we bombard these electrons at the surface of metal, the anodic metals, the positive charged metals. And these high-speed electrons interact with the metal and give off X-rays. This is the basic principle actually. We are going to study in bit more detail how what is the basic physics behind their generation. And one such device that generates X-rays are the hot cathode tube that also works on the same principle. They have a hot cathodic filament, as we can see, and what it actually does is we provide current in we provide voltage like in the thousands of volts, and then the electron beams hit this anode. There we get the X-rays in all directions, and then we collect the X-rays at a particular direction, 90 degree, because at that particular angle we have the highest intensity of X-rays without too much background noise or background radiations as well. And we know that if we are going to use more voltage across the cathode and anode, then the X-rays that we are going to get are of the very, very small wavelength and very high energy. And if we need more intense X-rays, we have to provide them with the more current, more intense X-ray. The thing is that if we are going to use more current, then more intense X-rays are going to get. But anodes will start to heat up a lot, and it can melt easily. So to tackle this problem of melting away of the anode, we use rotating anodes so that once the particular point of the anode which have been used in generating the X-rays could be reused again, it could be cooled down. And so we use rotating anode. As you can see, this is a diagram of the rotating or cathode tube. And mostly we rotate this anode at the RPM of 3000 to 6000, and Axes are not given off in one particular direction, but they are given off in all the direction. It is isotropic, not equal, but like it's in all directions it is given off. Maybe we only want to study in this particular direction, then we took that particular chunk of the X-rays. Now we got X-rays in different directions. So how do we get the one concentrated beam? So we have to concentrate it, right, to study so that we can focus it on our crystals, on our tissues for the X-ray therapies as well. So we are going to focus this all different directions X-rays onto one particular point, one particular frame. So we can do this using optics, using the various mirrors like ellipsoid mirrors and the glass fibers. We can use a single layered mirror or multiple layered mirror as well. As you can see, this is the image showing how the X-rays are given off in all directions. Using an ellipsoid mirror, they are being concentrated at one particular focal point. And this is the single layered mirror, and this is the multiple layered mirror. Now we are going to study in bit more detail about the what different kind of X-rays we are going to get, and what is the basic principle behind the generation of the X-rays, like in bit more depth. Now this is the X-ray spectrum that we are studying for, that is generated from the Howard cathode tube, in which the X-ray intensities have been studied as a function of accelerating voltage. As you can see, voltage is 15, 20, 25 kilovolt, and much more than that. And as the voltage is increasing, so does the X-ray intensity is increasing. So the spectrum, it is the whole spectrum of the X-rays that we are going to get from the cathode ray tubes. It consists of only two parts. One part is consists of the white radiation, which is a very bulkier part, a very wider part, this part, and very characteristic fine line spikes, very high energy spikes, very intense spikes, they're characteristic radiation. So we got these two different radiations via two different principles of their generation. So we are going to study about these two in a bit more detail. So white X-rays, thus as we have white light, which is composed of various radiations of different wavelengths. As we all know that white light have like 400 to 780 nanometers of wavelength from Vibgyor. We all know that, right? That our white light is composed of these seven colored radiation. Similar to this, the white radiations that we're going to get in the X-rays also composed of different wavelengths of X-rays, and they are actually arises when the high speed electrons are very like highly accelerated electrons comes in interactions with the atom, striking atom. Electrons that are given off by the cathode, we have a cathode, it's shooting out the electrons at the anode. The anode has atoms. As we can see, this is the nuclei, this electron cloud, and these electrons interact with these atoms. The electrons that are coming out of the cathode interacts with the atoms of the anodes. These interactions are mostly the electrostatic interactions, and these electrons actually decelerate because these forces could be attractive or repulsive in nature, and this deceleration of these high-speed electrons gives rise to the X-rays, as we can see. And this resultant spectrum is very broad. It is like this broad, like very broad spectrum, not the spikes. For the spikes, we need a particular wavelength, like one wavelength, very fine, like narrow width of wavelength. And if we want more intense white radiations, then we have to increase the voltage. The spectrum of white light doesn't depend on the which target material we are using. No. It depends on the how fastly, yeah, how much deceleration of excuse me, how much deceleration of the white of the highly speed, yeah, highly accelerated electrons is taking place. And these white radiations we are going to get, then the energy of this X-ray is actually directly proportional to the potential that we have used, the voltage that we have applied between the anode and the cathode. As we can see, maximum energy that is possessed by the X-ray is directly proportional to the applied voltage between the anode and cathode. Here E is the quantum charge, use the maximum voltage, and as we all know that energy equals to h nu equals to c by lambda. So we get the minimum wavelength that we can get for the white radiation equals to Sc by E maximum, or Sc equals to E by U. Mostly, generally, that the voltage that we applied between the anode and cathode, they are in the kilovolts. So we can modify this formula as the lambda minimum could be equal to 12.4 by U angstrom. And if we are using the very high voltage, like 30 to 460 kilovolts, then our lambda minimum is going to be less than 1 angstrom. Now, the second X-rays that we are getting, second part of the X-ray spectrum is the characteristic radiation. As we can see in the earlier photograph, here, these are the characteristic radiation. So how do we get these? There's very like they're very peculiar kind of X-rays, we can say. They are actually arise when we have like very highly energized, they are very high energy electrons. They knocks out the electron from the innermost shell. Yeah, and very like ultimate shell of an atom. Electrons get evacuated from there, and that creates a vacancy. And these vacancies are filled by the electrons from the higher shells like K shell, L shell. Sorry, the vacancies are created in the K or L or M shells, and the electrons from their higher shells, let's say L shell, M shell, N shell, they occupy this space. They fill up these vacancies, and this transitioning from the outer energy shells to the inner energy shells is what is responsible for these X-rays, these characteristic X-rays. And these X-rays are like very, very sharp peaks we are going to get because the energy gap between two shells is very quantized in nature. And the spectrum is mostly dependent upon the metal we are using. Like depending on the metal target, they would have a different L, M, N spacing, right? So depending on that, we are going to get different energies of X-rays. The energy of the characteristic X-ray that we are using is directly proportional to the target metal. How heavy the metal is going to be, the heavier the more energy of the X-rays we are going to get. Or we can say it is inversely proportional to the 1 lambda minimum of the characteristic wavelength. And as we know that the energy gap between the different shells and subshells in an atom are quantized, so L characteristics equal to Sc by delta E because energy is equals to H nu is equals to Sc by lambda minimum, and lambda minimum equals to Sc by delta E. Delta E is the energy difference between the higher energy shell from which the electrons are transitioning to the lower energy shells. And there is a selection rule. Not all transitions are allowed. For the allowed transitions, delta L value for the particular shell should be plus minus 1. In the medical field, for the medical X-rays that we got done, the X-rays that we are used are the tungsten KFR radiation. And in the XRD, mostly we use the either the copper or the molybdenum K alpha X-rays. So yes, let's now talk about the Seaborn's notation of the X-rays. Now we have studied about earlier we saw there's something K alpha was written somewhere, K beta was also written somewhere. So what are these like what are these numbers actually like signifies? So these all are actually part of Seaborn's notations of the X-rays, bit outdated model, but we still use this model to characterize the X-rays, mostly the characteristic radiations. Generally, we can write it as the NMP and is the principal quantum number to the shell from which the electrons have been ejected by the high-speed electrons, the shell to which the electron transitions are occurring. Most of, like generally, it is actually the K shell, the innermost shell. We all know that in the early classes we have studied that we have K shell, L shell, M shell, dot dot dot, and like so on. M is the relative position, like which shell from which the electron transitions are taking place. Like if we got electrons out of the K shell, then the electrons are coming from L shell or M shell. If electrons are coming from the K L shell, then there's only one gap, so it is alpha. If, it is coming from M, then there's two. Like there's two energy shells in between, so it is beta, like second shell. And the P actually symbolizes when there is a spin orbital coupling between the then there's spin orbital coupling, then the different states we got different energy levels actually. As we know in the term state symbols, we know that J value, right? From the spin orbital coupling we get. So like we can get 2p1 or 2p2, something like that, 2p3, like something like that. They have a very similar energy, but this is ground state term symbol. This is like steady state term symbol. So like higher energy state term symbols. This has more intensity than this one. So these are the different energy levels of M actually. And this actually arises from the spin orbital coupling and actually N are the principal quantum number from K, L, M, and M are alpha, beta, gamma, the relative position of the shell from which the electrons transitions are occurring. P are just 1, 2, 3 after talking about the different energy level splittings. There could be L radiations, but they are very rarely used in XRD because of their very low yield from the whole cathode tube in comparison to the K radiation of the somewhat same wavelength. Let's say this is our K shell, this is our L shell, M shell. So electrons go out from this, creating vacancy, and electrons coming from here. So then this is what electron transitions are occurring in the K from the one shell which is right next to the K, that is K alpha, and 1. If say that if it has been splitted into the any other signals, if it is splitted into 1 and 2, you get it like this. So it's like this only. And sometimes these have a very similar energy. We take their average as well. So we write it as K alpha bar. So we're talking about the copper radiation that we mostly use in XRD. These actually like the copper has very very clear spectrum. Like white radiation is very very less there, and the wavelength is actually longer. It is 1.5 angstrom we are getting, which is the average of K alpha 1 and K alpha 2 because K alpha got split into K alpha 1 and the K alpha 2 due to spin orbital coupling. It is better for the XRD due to the stronger resonance scattering and useful for determining the absolute configuration of chiral molecule and large molecules. And the other X-rays we are using the molybdenum ones. They have very short wavelength, like zero point 0.7 angstrom, almost the half of the copper, used for the units such as smaller or the better scattering. And they're very, very weakly absorbed by the metals atoms whose like atomic number is more than 25. As the energy of the X-rays increased, so that their penetration power also increases, means they won't be get absorbed by the particular metal, particular atomic, nuclei, atomic substances. They will either get scattered or pass through them. And this was about the molybdenum X-rays. Now, the generation of monochromatic beam of X-ray. Now, the X-ray that we have gotten, they are continuous in nature, means they are composite of various wavelengths, but we need only one particular wavelength. We use a monochromatic source. Like we all know that we have the white radiation, a white light, let's say in the visible light, talking about white light. We just want to use the red light. So we have to cut out all the remaining six that different wavelengths. So this is what monochromators are used for, because we don't want to like all those wavelengths to like hamper our analysis. This is the we use the X-ray filters for them. So we are using a continuous X-ray source. Let's say this is the cathode tube, and we are getting X-rays. We are passing through the filter, and we are getting only one particular wavelength that we needed. And to convert this continuous beam of X-rays into the monochromatic light, we use X-ray filters or X-ray monochromators. They are mostly optical devices or maybe some other instrumentations, yeah, other materials as well, like say graphite or crystals as well. So, if we're talking about the absorption of X-rays by particular metal or particular substance, so as we all know that the absorption is inversely proportional to the wavelength. As the energy of the particular X-rays are increasing, so does their penetration power, and hence the absorption decreases. As we can see here, the wavelength, it is the absorption spectrum of the X-ray for the copper. As the X-rays lambda is decreasing, so does the absorbance as well. But there comes a point where the energy of the X-ray is equals to the energy that is required to remove the electron from the ultimate shell, from the K shell. Then at that particular time, the electrons absorbed from the K shell absorb the energy and get ejected out. This is called K absorption edge. This is the K absorption edge of this copper lies between the K alpha of the copper and K beta of the copper. And the X-ray filters that we are going to use, we are going to design are based upon this K absorption edge. So we are going to exploit this. Let's say we are using copper X-rays filtration. So we use nickel. So what does nickel have actually? Nickel's absorption as lies between the K alpha and the K beta range of the copper. So nickel will filter out the K beta and K alpha. So nickel actually absorbs K beta much more, like almost 6 times more rapidly and more readily than the K alpha, giving us the K alpha only and removing the K beta. Same goes for the molybdenum as well. We're using niobium as the filter. So generally, if we have the X-ray of the Z atom and we have to create a filter, we use Z minus one atom, Z minus one metal element to create a particular filter. So from this diagram, actually, we can actually understand what I'm talking about. This is the absorption of X-ray by copper. It is decreasing as the wavelength increasing, but here comes the absorption as for the copper increasing, then it's further decreasing. And near this edge like the K alpha and the K beta. Now, if you are going to use nickel, then this K beta of the copper gets absorbed by the nickel K as leaving the copper K alpha only. So we are only going to get the copper K alpha because the nickel K as lies between here, somewhere here in the middle, somewhere middle of the 1.4 and 1.6. So now, the second layers that we use are the X-ray chromators. X-ray chromators are the devices that actually what they do is actually they take the continuous ray of X-rays. In this case, we are using graphite crystals as the monochromators, and they diffract these X-rays at a different angle. Let's say this particular angle of the X-ray we needed. This is our monochromatic beam of light we're going to get. Let's say we just want to use this particular wavelength, a particular lambda of X-ray for our purposes. So this is basically like a prism that we use, right? We use white light and pass it through the prism. We get different spectrum, right? From Vibgyor we are going to get Vibgyor, just want to use the red, then we are going to use this angle. We are going to set up our sample somewhere here, and then we are going to collect the red light only. Similar to this, we are using monochromator. which is the graphite crystal in our case. X-rays are going to get diffracted by this, and at a particular theta, we are going to get our interest of X-rays. Now, the last topic for this presentation are the synchrotron sources. What are synchrotron sources? Actually, synchrotron sources actually they are nothing but the evacuated pipes. They are like curved into the rings, and in which the electrons are subjugated to the high speed high speed movement actually. So we take the electrons, we inject them into these hollow tubes and accelerate them in loops, like at the speed close to the speed of light. Then we're going to use magnet because electrons being the electrical entity have a charge. They're going to have magnetic field as well. They're going to interact with the metal magnet as well. So they're going to change their trajectory. Either they're going to change their direction or either they're going to change the speed, and due to which we are going to get X-rays because whenever there is a charged entity at the high speed it's moving, its momentum is changing, so we are going to get some radiations out of it. And these radiations that we're going to get out of it are the X-rays, and they are like very, very high intense, like billions of times more intense than the X-rays we're going to get from the whole cathode tubes. And we can use them to study the crystals that are very, very fine, like whose edge length are like micrometers and millimeters, like very, very small edge length. And this is the synchrotron facility that they have in the UK. This is UK's national synchrotron. Thank you everyone for listening. This was from my side. This was my assignment for the course CML 661. My name is Sachin, and I wish you all good luck.